An astonishing breakthrough from the James Webb Space Telescope has revealed what seems to be artificial illumination in the vastness of space, approximately 7 trillion miles from Earth. This extraordinary finding has sparked tremendous interest regarding the possible existence of sentient life beyond our planet. The telescope directed its attention toward Proxima Centauri b, the nearest known exoplanet to Earth, and detected unusual luminous emissions radiating from its surface. What could explain these city-like lights visible on Proxima b and the nearby planet Tauri b? Could this point to the presence of intelligent beings far beyond our solar system? We delve into how the James Webb Space Telescope uncovered these exceptional anomalies scattered across the cosmos. For generations, scholars and inquisitive minds alike have contemplated the existence of alien life. Any signal that might affirm this long-standing hope has always inspired excitement. Recently, top scientists were stunned when compelling indications of life beyond our galaxy were transmitted back to Earth by the telescope. It observed unmistakable urban-style flickers emanating from Proxima Centauri b. These gleaming signals strongly resemble the lights of a distant cityscape. The idea that an extraterrestrial civilization could inhabit this far-off world has captivated the scientific community. Researchers are intrigued and even unsettled by what may be the discovery they've awaited for decades, if confirmed. As many speculate, this would suggest that intelligent alien societies are building advanced civilizations in places we are only now beginning to perceive. Reflecting on this interstellar glow originating some 7 trillion miles away, NASA experts are now considering how long these lights might have been active, waiting silently until our technology advanced enough to observe them. Astrophysicist David Kipping of Columbia University called Proxima b mesmerizing. He attributes the planet's glowing behavior to the chaotic thermal patterns of its nearby star system, our solar system's closest stellar neighbor, which deviates significantly from typical planetary behavior. Normally, rocky planets absorb light from their stars and re-emit it as infrared heat, yet Proxima b defies this pattern. Its infrared signal differs starkly from its host star, Proxima Centauri. This stands as a major discovery by the James Webb Space Telescope. With its ability to detect infrared wavelengths and analyze Proxima b's thermal emissions, the telescope is crucial to decoding the mysteries of this exoplanet's atmosphere. Using its sophisticated infrared sensors and high thermal precision, astronomers plan to further study Proxima b's atmospheric layers and evaluate its potential for habitability. The telescope's sensitivity to faint infrared light allows it to observe the night side of Proxima Centauri b, capturing even the weakest signs of illumination in deep space. While this would typically be an obstacle for most observatories, this telescope was engineered to detect even the slightest radiative signals. It is ideally suited to investigate any possible artificial light sources on Proxima b's dark hemisphere. Artificial lighting in space is rare, and distinct it falls within a very narrow band of the light spectrum, much narrower than that of natural starlight. Proxima b displays a notable link between its observable traits and the physical features on its surface. Scientists speculate that its sunlit side could host large solar energy collectors, absorbing power from its nearby star. As Proxima b revolves around Proxima Centauri, it undergoes day and night cycles much like Earth's, experiencing intense heat during the day and cooling off during the night. Temperature swings on Proxima b are influenced by its physical makeup. If the planet lacks an atmosphere, the temperature difference between its hemispheres would be dramatic and instantaneous. Without atmospheric gases to moderate heat, the sun-facing side would become blistering hot, while the other side would freeze in total darkness. Understanding these temperature patterns is key to learning more about the planet's climate and surface conditions. Thanks to the telescope's ability to detect subtle thermal variations, scientists can better study the planet's unique behavior and climate dynamics. Interestingly, the telescope's orbit around Earth is synchronized with Proxima b's rotation, enabling it to observe both its daylight and nighttime phases within just 11 point-to-Earth days. If Proxima b indeed possesses an atmosphere, Researchers will next aim to analyze its chemical composition, searching for elements that could support life, such as oxygen, water vapor, and methane. Detecting these vital compounds requires astronomers to examine how light travels through the planet's atmosphere. This is no simple task, even for such an advanced instrument. The telescope is currently our best tool for probing exoplanetary atmospheres, though it can only perform detailed studies on a select few nearby worlds. As scientists expand their focus to larger ground-based observatories like the extremely large telescope belt, expected to begin operations by 2028, the ability to explore the chemical signatures of distant atmospheres will grow. The ELB may offer new insights into whether these distant planets could support life. Researchers across the globe are eagerly anticipating the launch of even more powerful space telescopes. Until then, this telescope remains essential to our search for life beyond Earth. Despite its technological limits, the telescope continues to uncover discoveries that reshape our understanding of the universe. One of the core goals of the next generation of space instruments is to reduce the glare of host stars so that astronomers can study the faint reflected light from orbiting exoplanets. This could be achieved with internal starlight blockers or large space-based shades, like shielding your eyes with your hand to see a dim object more clearly. Reducing stellar brightness will allow scientists to isolate and analyze weak planetary light, offering clearer insight into climate and habitability. However, this method comes with its own hurdles. Experts must distinguish between gases released by biological life and those from geological processes, such as volcanic eruptions. Researchers are refining their techniques to avoid mistaking false positives for true signs of life. This telescope gives us a glimpse into the remarkable possibilities that lie just beyond our reach. As our exploration of space becomes more sophisticated, we are gradually uncovering the universe's complexities and rethinking humanity's place within it. Although countless celestial objects have been studied, none have definitively shown signs of life yet. The search continues with renewed energy. For ages, we have wondered if we are alone in the universe. That question still drives scientists today. Currently, researchers are employing this telescope to examine distant planets for signs of alien civilizations. There is growing speculation that extraterrestrial life might already exist among the stars, perhaps waiting to be discovered. To help resolve this mystery, two American astronomers, Jill Tarter and Thomas Pearson, launched the search for extraterrestrial intelligence SETI in 1984, managed by the SETI Institute. This nonprofit project scans the skies for radio signals that could come from other worlds. Radio waves are ideal because they can travel immense distances through space with minimal interference. This makes them more likely to be detected by the 42 radio dishes of the Allen Telescope Array in California's Cascade Mountains. Despite listening for over 3 decades, SETI has yet to capture a confirmed alien signal. Still, Tarter remains optimistic, envisioning a future where everyone on Earth could take part in the search for intelligent life. That optimism gained new momentum when reports surfaced that the telescope had detected SETI-like lights from a planet not far from our own. This space telescope is the most powerful scientific tool humanity has yet launched into orbit to probe the secrets of the universe. Since its deployment in December 2020, it has been regarded as the most advanced infrared observatory ever created. Its optics can penetrate cosmic dust and unveil hidden features across the cosmos. Its primary mission is to observe the earliest galaxies and stars that formed more than 13 billion years ago. Named in honor of NASA Administrator James E. Webb, a key figure in the Apollo missions, the telescope carries a remarkable set of instruments: a near-infrared camera, a spectrograph, a mid-infrared imager, and a fine guidance sensor for pinpoint accuracy. Its massive mirror, composed of 18 gold-coated hexagonal segments, is designed to capture faint light from the most remote regions of the universe. It operates at extremely cold temperatures, allowing it to detect even the weakest thermal signals from faraway worlds. Since its launch, the telescope has delivered stunning imagery of stellar nurseries, merging galaxies, and a vast range of previously hidden cosmic phenomena. Through its extraordinary capabilities, it continues to transform our view of the universe. This telescope stands as a milestone in humanity's quest to explore the cosmos. Its unmatched accuracy and sensitivity make it a central figure in our efforts to understand how stars, planets, and potentially life evolve throughout space. As observational technology advances, future telescopes may eventually surpass its capabilities. These next-generation instruments might not only detect life-sustaining elements, but also capture visual proof of alien civilizations, possibly even structures or technological activities.